Today, we are diving deep into a truly fascinating story from our celestial neighborhood. We're going to unpack the incredible science behind a visitor from another star system, the interstellar comet 3I/Atlas. So, this comprehensive analysis was put together by Nohil Kodiyatar and co-author Abhay Shamala. Their work pulls together a massive amount of research, and we're about to jump right into their key findings.
All right, here's our roadmap. We'll kick things off with an introduction to this new visitor. Then we'll cover its discovery and first light. After that, we'll get a spectacular view from space, decode the comet's physics, and then touch on some really modern challenges in science, ethics, and AI. We'll wrap it all up by looking at why this campaign sets a whole new benchmark for astronomy.
Okay, let's get right into it. The detection of 3I/Atlas was, and I don't say this lightly, a complete game changer. It was first spotted on July 1st, 2025 at an incredible 5.2 astronomical units from the Sun. Now, to give you some perspective, that is more than 5 times the distance from us here on Earth to the Sun. This super early detection gave astronomers a head start like never before, letting them study it in way more detail than any previous interstellar object.
And because of that early catch, the observation campaign was just unprecedented. By the end of October 2025, researchers had collected a staggering amount of data. I mean, just look at this. Over 3,000 astrometric positions, almost 200 light curves, 43 spectroscopic datasets, and 9mm interferometric tracks. It's this sheer volume and variety that makes the study of 3I/Atlas so incredibly groundbreaking. And what's really crucial here is how all this data was handled. It was all done with the highest standards of open science. Everything adheres to the FAIR principles, which means it's findable, accessible, interoperable, and reusable. It's all publicly available in the NASA and ESO archives for anyone in the world to study. Okay, so let's rewind a bit. Section 2 is all about the discovery itself, and those initial observations that gave us our very first clues about this mysterious object. The discovery credit goes to the Asteroid Terrestrial Impact Last Alert System, or ATLAS. It's this network of telescopes that's constantly scanning the sky. The timeline of the discovery is just a perfect example of modern astronomical efficiency. At time 0, the ATLAS telescope in Chile snaps the first images. Just 6 minutes later, an algorithm flags it as unusual. Then, in under an hour and a half, a sister telescope in Hawaii confirms it. And get this, only 5.8 hours after that very first photo, the official announcement went out. That is the fastest interstellar object announcement ever. Of course, as soon as the word was out, other powerful telescopes jumped in. The 4.3-meter Lowell Discovery Telescope captured its colors. What you're looking at here are the color indices. They basically tell us how much light the comet reflects at different wavelengths. And that gives us some really important clues about what its surface is made of. So here's the key takeaway. How does 3I/Atlas stack up against the other interstellar objects we've seen? Well, with a BV index of 0.98, it's right in the middle. It's redder than 2I Borisov, but it's bluer than the very reddish 1I Oumuamua. This tells us its surface is probably pretty different from the interstellar visitors that came before. Now, as great as ground-based telescopes are, to really understand this object, we needed to get above our atmosphere. So our third section is all about the crucial data we got from the Hubble and James Webb Space Telescopes. This is where we got an absolutely unparalleled view of this thing.
On September 10, 2025, Hubble locked onto 3I/Atlas, and what did it see? It saw a coma, that's the fuzzy cloud of gas and dust around the core, stretching about 4,900 kilometers across. Its brightness profile suggested a really steady, even outflow of material. And, importantly, Hubble didn't see any signs of distinct jets, which sometimes erupt from a comet's surface.
But, you know, the James Webb Space Telescope might have delivered the most stunning result of all, and it can be boiled down to this single number right here. So what does greater than or equal to 1 actually mean? Well, it's the ratio of carbon dioxide production to water production. JWST's instruments were able to measure both gases coming off the nucleus. And just as this key finding from Berlin and their colleagues says, this really high ratio of CO2 to water makes 3I/Atlas fundamentally different. See, most comets in our solar system are driven by water ice. This tells us that 3I/Atlas, so far from the Sun, was being powered mostly by sublimating carbon dioxide ice. It's a huge clue that it might have formed in a very different, maybe much colder, star system than our own. So, with all this incredible data in hand, what's next? Well, the next step was to make sense of it all.
And in our fourth section, we're going to look at how scientists used some really sophisticated models to decode the physics of what was actually going on with 3I/ATLS.
To figure out what was happening with the dust coming off the comet, scientists used a classic technique called the Finson-Probstein model. Basically, they took a great image of the comet's tail from the Canada-France-Hawaii telescope, and by analyzing its shape, they could work backwards to figure out the properties of the dust itself. They found the particles were tiny, about 1 micron, and were being pushed away from the nucleus at about 120 meters per second.
Another really important piece of the puzzle is what's called the active area fraction. This tells us what percentage of the comet's surface is actually active, where ice is turning straight into gas. And for 3I/Atlas, that number is really small, just 0.8%. This fits perfectly with the idea of a surface that's mostly covered in a thick layer of dust, with gas escaping from just a few active spots.
You know, the story of 3I/Atlas isn't just about the comet. It's also about the process of doing science in the 21st century. So this section dives into not just the subtle forces acting on the comet, but also the very real, very human challenges of managing data and communicating discoveries in the age of social media.
That discovery of high carbon dioxide levels, it created a bit of a firestorm online. In just 24 hours after the data came out, there were 1.2 million posts about it on X. And as you can see here, almost half of them, a staggering 47%, completely misinterpreted the science, making these wild claims about alien gases.
So, what do you do about that? Well, the science team actually deployed an AI tool called AstroBERT v2. It was designed to automatically reply to posts containing misinformation with links to the actual public data. And the result? It cut the retweet speed of these false claims by 62%. It's a pretty powerful example of using AI to help protect scientific integrity.
And that brings us to our conclusion. The whole campaign to study 3I/Atlas wasn't just about learning about a new object. It really set a new standard for how we conduct and share astronomical research.
The achievements here really do speak for themselves. The earliest detection ever for an interstellar object, the widest spectral coverage, the fastest data release, a super precise measurement of its tiny non-gravitational forces, and maybe most importantly, an absolute commitment to open science. And of course, this was a massive collaborative effort. As you can see, so many different teams and tools contributed to what we now know. From those groundbreaking observations with JWST and the VLT, to the innovative software and AI that helped make sense of it all and fight misinformation, every single piece was essential.
And of course, work like this always stands on the shoulders of giants. Here's just a small sample of the key references, including some of the foundational papers on things like dust modeling and fair data principles, right alongside the brand new publications on 3I/Atlas itself. The full list is of course available in the source publication.
And so we're left with this tantalizing glimpse into the future of astronomy. The study of 3I/Atlas didn't just reveal the secrets of an interstellar visitor, it also gave us a whole new playbook for how to do science in a more open, collaborative, and responsible way. So I'll leave you with this question. When the next cosmic traveler comes visiting, how will these new benchmarks shape what we're able to discover? Thank you for listening.